Howdy everyone, this is Mr. Palmer with Bowtie Physics. Today, I want to continue our conversation about work and energy and discuss the conservation of energy. Recall the work-energy theorem from our last class, which states that the net work done on a system results in a change in energy to that system. It is important to clearly define your system, since only forces outside the system can perform work. If you define your system to have no outside forces, then there is no work done, no change in energy, and therefore energy is conserved in that system. So let's take a look at some examples. If you define your system to be the entire universe, which you're allowed to do, then there are no outside forces to perform work. That means that this is an isolated system with no work done by forces outside the system, no change in energy inside the system, and indeed, energy inside the entire universe is conserved. However, it takes many forms, such as nuclear, electrical, thermal, and mechanical, along with a slew of other energies. It's complicated. So let's refer back to a simpler example from our projectile motion unit, an object in freefall. Recall that the only forces acting on an object in freefall is the force of gravity. If we define our system to be just the ball, then its weight, the gravitational force of the Earth acting on the ball, is an outside force that performs work on the ball and changes the energy of the system, specifically the kinetic energy. We could also define the system to include the ball and the Earth, so that the force of gravity between the Earth and the ball is included in the system, as is the Newton's third law pair of the force of the ball acting on the Earth. Since both forces are internal and there are no external forces, that means that there is no work done on the system and zero change in energy. But wait, what about the force of gravity that performed work in the first situation? When Earth is included in the system, the force of gravity becomes an internal force, and it performs no work. Instead, it is conserved within the system as stored or potential energy. We can think of potential energy as the energy stored by gravity when work is done against it. Plugging in the expression for work, we find that the potential energy due to gravity is the opposite of the force of gravity times our vertical displacement times the cosine of the angle between them. If the vertical displacement of the ball is downward in the same direction of gravity, such that the angle between them is zero, then gravity does positive work, which results in a decrease in potential energy. However, if the vertical displacement is upward against the force of gravity, then the angle between the displacement and force vectors are 180 degrees, which results in the negative work done by gravity. Looking at our original definition of potential energy, if the work done by gravity is negative, that then results in a positive gain in potential energy. We can simplify our expression for gravitational potential energy by focusing on positive vertical displacement, which results in a positive potential energy, which is equal to the force of gravity, mg, multiplied by that positive vertical displacement, which is commonly called height. And there you have our common definition for potential energy. U equals mgh. Note that gravitational potential energy is only considered because we define the ball and Earth to be part of our system, so that the force of gravity is internal to our system and conservative. Only conservative forces can store potential energy. We've seen with the force of gravity that by lifting an object to a certain height, we can store energy within the system. Later this unit, we'll look at elastic potential energy, such as rubber bands that store energy when stretched, or the force of a spring that stores energy when stretched or compressed. Let's take a look at a visual example of the conservation of energy. Here we are with the Energy Skate Park simulation from the University of Colorado Boulder and PhET. This will allow us to see the energy involved with this skateboarder. If we define our system to be the skateboarder and the Earth and neglect the force of friction, we then have 0 outside forces to perform net work, which results in 0 change in energy. Our system will be conserved, and the total energy will stay the same. Looking at the simulation to the right, the skateboarder is stationary at the top of the halfpipe. Since they're not moving, that means their kinetic energy is 0, but they are off the ground, so their potential energy due to gravity is equal to mgh, which accounts for their total energy at the top of the halfpipe. When the skateboarder drops in, energy transforms from potential energy to kinetic energy and back again. Since there's no force of friction to do work and remove energy from the system's energy is conserved. If we pause the skateboarder at the bottom of the ramp, we can see that the potential energy at the bottom of the halfpipe is 0, yet the energy has stayed within the system with the same total energy and has just transformed to our maximum kinetic energy. No matter where the skateboarder is in the halfpipe, the energy of the total system remains the same. It's just a combination of the kinetic energy of their motion plus the potential energy of their position above the ground that results in a conserved constant energy of the system. I hope this demonstration helped visualize the conservation of energy and made your understanding a bit more complete. Let me give you something to think about before class tomorrow. What would happen to the skate park system if we did introduce friction? How would that affect the energies of the skateboarder and Earth system? I'll leave you to think about that until next time. Signing off.